Hello and welcome back to differential equations. We are going to talk about numerical approximations, numerical solutions to differential equations. And before we get there, and I write these formulas from three sections on numerics, which is Euler, improved Euler, and Runge-Kutta methods, we are going to briefly talk about old versus new. Meaning old is calc, and so old would be calc, and new being differential equation. The first difference, which I asked you before, was that, and you answered correctly, right, was that in calculus, all numerical methods we did gave us a single number answer. And that one number was either a root of a function, which was Newton's method, was area under the curve, which were all of those Riemann sum with rectangles, Simpson, trapezoid, and so on. Or it was a value that was computed through Taylor series approximation. All of which you can code with loops, all of which take a number and improve that same number over and over and over with how many iterations you want to have. So in one case, we had a code written by Mike who went 100,000 calculations, but there was 100,000 improvements on the same number to spit out one number, which was area under the curve, right? So old was one number solution, improved on with repeated calculations. And we can, think of any one of those from before. Now, new for differential equations is going to be that we have to keep every calculation stored as x comma y, so we can plot the curve. So what's the difference? Curve is the answer. Remember that the answer to the differential equation is the equation. Usually I say function, but equation is much better answer, right? Because you can have implicit formulas as answers which are not functions, and you have encountered many of those in your homework assignments so far. So this is what the difference is, right? The first method for 2.4 is the Eulers method. So welcome to being, 250 years behind with this, maybe more, 300 years behind with this one, right? And this method is going to take a value, it's going to take differential equation, it's going to take initial value that it's given to you, and you are going to start your calculations from there. Hopefully you will try and code this into a loop and have the code working. So here is the algorithm, right? The algorithm is what you are coding. So in red, right? Algorithm is the follows. Given differential equation, not differential equation, given initial value problem, dy dx equals f of xy, with initial value x0, y0. Euler's method with step size h, and I'm going to underline that. Consists of applying the iterative formula yn plus 1 is equal to yn plus age times of f of xn comma yn for n larger than 0, clearly because your n is the counter 1, 2, 3, 4. To calculate successive approximations y1, 2, y2, y3, and so on. And then eventually you can get the stuff. So this is what's important to. Well, you thought I was joking, right? All right. So this is it. This is what you get to code, and your step age is a variable that would be adding to the x value to move your calculation forward. Now, I haven't done derivation for this, but I am going to write also as a part of this, if you are going to use this and really try to code it, it needs to be also read. Xn plus 1 is xn plus age. So your step size is the one that advances age. And if you want to be very precise, you are keeping that age small. So 0.1, 0.01, 0.000001, right? And remember that if you are trying to do the solution for the interval, let's say 2 to 3, and your step size age, let's just write that. So interval, let's go 2 to 4. Interval 2 to 4 with step age equals 0.1 will have how many calculations? Well, your first calculation here is x0 equals 2. And then your next calculation will be x1, which is 2.1. Then the next one is x2, 2.2. Because every next calculation is going to change x from x to x plus age. So how many calculations am I going to have on the interval 2 to 4? 20 calculations, right? So be very careful, right, with your arrays and storing all of these, because I need to keep every calculation. You have your x0, you stick that into the equation up there, you calculate your y, well, sorry, x0 and y0 are given. That's x0 and y0 are given. You see that that's given to you. Differential equation is given, which gives you the function that you will be, and you can hard code the function in. That's you don't have to come up with a way to input the function and so on. Just hard code one example. You can add fluff later if you care, right? Maybe for computer science, I can make it mandatory. Yeah, ask for input, right? Then you have to do the scans and everyone else, just to be annoying, right? Because the rest of the course is useless to you, all right? Computer science, today's your day, all right? The rest, you just pass it, all right? So x0 and y0 are given to you, and this thing is given to you in the differential equation. You are coding that one here, and you are asking for input from the array for x0, right? And so x0, and here are all of your x's, right? So it's going to be 20 calculations. Just for these, right? Stored in some kind of array, and then you will just be assigning the y values to each in the same array. Now in array, we know that the first value in array is 0 anyway, so it lines up with our coefficients anyway, so it's going to be awesome. We don't have to worry about any of those things. So let's do an example of this on paper, and obviously then you are just, challenged to work out. So I'm just going to go into the homework. And I'm just going to pick problem number 4 because it's easy to compute these things and I don't want to be bothered, all right? Because this is not something that you should be computing by hand. Y prime is equal to x minus y, and y of 0 is 1. They say the solution on the interval 0 to 1/2, first with a step size of 0 to 5, and then with a step size of 0.1. So it's like 2 calculations. A, step size is 1/4. That's going to be 2 calculations, right? And then B, age equals 0.1. All right, that's it. Now, we know that 1/2 is 0.5, so we'll live with both of these. So to do Euler's method, we are going to start with x, so part A. x0 is 0, y0 is 1. And now I have my Euler's formula, which said, well, I can write it here, yn plus 1 is equal to yn, right, which is the current one, plus age times f of xn, comma, yn. So this formula is going to change into y1 is equal to y0 plus why did I put age as 0.24? So 0.25. 0.25 times, and over here you're going to have x0 minus y0. So when my n is equal to 0, that's what I have as a first calculation. When my n is equal to 0, the first y value I get is going to be n plus 1, which is y1. So now this calculation, when I plug numbers in, is going to be y of 0 is 1 plus 0.25 of x0 is 0 minus y0 is 1. So we get 0.75 as the answer, right? When you do the calculation, that's basic arithmetic. Now you have to store your y1 in array and then repeat the process for the next calculation. The first calculation is done. My first point was 0, 1. My second point is what? Well, the step size age increased my x0, which was 0, to 0.25, and the calculation gave us that y1 is 0.75. Now we are ready, right, to solve the next stage. y2 is going to be y1 plus 0.25 of x1 minus y1. So all of the n values from the formula are now increased by 1. Java-speaking people, I++, right? You increase the counter by 1. So you are going to now pick up the values of y1, x1, y1. Well, they're right here, right? This is your x0, y0. This is your x1, y1. That's what they are. So now you just plug these two numbers, stick them in there, and compute the y2. It's very simple, right? It's just busy. That's why we make the computer do this in a loop and not sit here for 15 hours computing by hand. 200 years ago, people did this by hand, 100 calculations on the candlelight, right? And you know when it flickers, what it does to your eyes? Yeah, right? And if they had no candle, then they take something shiny and reflect the moonlight, right, and do it. Because the rest of the day was digging in the field so you can eat, right? I know. And now you just toss away half a plate because you're full. y1, 0.75 plus step size, age, 0.25. x1, 0.25 minus y1, 0.75. Why is this x minus y? Because your differential equation was x minus y. That's the hard-coded because that is the equation you're solving. Different problem will have that something else, right? So when you're coding this, you can pick some problem from the homework and don't pick x minus y and just something simple. Take take something heavier, like they don't have anything heavier. E to the negative y, negative 3x squared y, right? So whatever. So now, what's y2? y2 is 0.75 plus I hate these decimals. Thank you. 3/4 plus 1/4 times negative 1/2. This is the way to do these things. It's just so that's 3/4 minus
3/8.
Yes, 1/8.
It's going to be 0.625.
So 6 5/8, right? That's the way to do it. Which is 0.625. Now your step size age increases by 0.25, so it's 0.5 on x coordinate, and you have 0.625 on your y coordinate, and these are your x2. And now we have to stop. We're done because they want the interval from 0 to half. Well, we reached the half on x. So time to bail, right? We got x2 and then y2. Now, what is your answer? I'll write it in blood. Your answer is not just the last point. It's all 3 points. Because when you plot all 3 points, you can draw a function or a curve. Maybe it's not a function, right? You draw through those 3 points. So your answer is, you can draw the table if you want x, y, and just plug them all in. 0, 1. Quarter and 3/4, and half and 5/8, or if you like decimals, 0, 1, 0, 2, 5, 0, 7, 5, and 0, 5, 0, 6, 2, 5. The entire table, and this is why I say the difference between what you coded maybe previously is you can just recycle the previous number and you don't have to keep it. Now you are still recycling them to calculate, right? Because all your y2 is calculated using x1 and y1. But we also had to keep x1 and y1 in the array for the later display. So that's the new. And now if you code the loop for this, obviously storing inside the array needs to be also in the loop. Calling values from the array has to be in the same loop. It's a single loop that you are coding, and then once the loop is done, 10 calculations, 20, 30 calculations, you just print the entire array because you need all of the points. So try not to have 100,000 points, right? Because this computer is just going to list 100,000 points. And then good luck scrolling. Right? Now, there are ways to make this, to add more fluff, which is ask for input, right? Which would input the function in the code and so on. But I'm asking you just to hard code 5 lines. Now, those of you that took MATLAB, if you don't speak Java, Python, or, I don't care which program you use. For me, it's important that you just try this and whatever. The code given for MATLAB, if you have access to MATLAB, you can just jump on page 114, 115, and literally learn nothing because the code is there, right? That's Control-C, Control-V, right? The trick is to try and code on your own and learn at least the basic loop for basic calculations later on. So that's that. They even have the TI-84 code given on how you would code that on a TI-84 calculator. Should work for 83 as well. So 84, 83 is the same architecture, just 84 has a faster processor. That's the only difference between the two. Everything else is the same. And more RAM. That's it. So whatever code works for 84 works for 83 as well. And yeah. You can get the emulator if you have the right phone. Nice one. They did a couple of examples in the book. Every time they give the table of values, just like, they give horizontal, I gave a vertical table, keeping all of the points from the calculation, and then they plot those points, which you can do in Excel. You don't have to code. That's another fluff you can add, right? One is to input the function, the other one is to produce the graph, right? Again, that's more for computer science than, right? But if you care to have some graphical user interface and stuff, right, you can do all of that. And then make sure you include it on your resume. And I'm not joking, because those things are extras that you did to show off your math skills, right? So you include that. You don't include that you are able to use Microsoft Word, because everyone is. You say that you coded, right, Eulers Method. So they say, oh, okay, right, there's a plus there. 2.4 is done. We can do part B to annoy ourselves with 6 calculations, right, on 0.1 step size age. So let's take a look at least a few of those. For part B, our step size age is now 0.1 instead of the other one. So we'll have, we actually have the step size when you divide, and then plus 1, because that endpoint has an extra calculation. So last time when I said 20 calculations, it was supposed to say 21 calculations, right? Because it's 20 calculations from 2 to 3.9. It's 20 calculation, and then calculating 4 is the 21st calculation. Be careful that you use that in a loop as well, right? your array needs to be large enough to accommodate for it. So same problem, same differential equation. Was it x minus y or y minus x?
X minus y.
Thank you. And we had our initial condition y of 0 is 1. Again, this over here spits out x0 is 0, y0 is 1. You have to be able to read initial condition.
So I got how you got the y array. What did you do with the x array to increment each time?
Plus age, right?
Plus h, right?
Yeah.
Okay.
So you have your x0, you steal it from there, and then plus age for every next cell. You have to put that as a line as well in the... Well, just read the age off of the...
It's
Yeah. And so we have our first calculation, right? For y1, it's going to be y0 plus age, and then we have x0 minus y0. So y1 will be 1 plus, previously we had 0.25. Okay, good. So now it's 0.1 for age. That's the step size. And then we have x0 is 0 minus 1. So you have 1 minus 0.1, which is 0.9. And if I am to store all of my values in the xy array, I have 0, 1 for the first, and now I have 0.1, 0.9 on the second row. y2 is y1 plus age, x1 minus y1. So y2 is, now, steal your x1 and your y1 from the table. That's going to be y1 is 0.9 plus step size age is 0.1. And now your x1 is 0.1 because it was x0 plus the step size age. So 0 plus 0.1, 0.1. Minus y1, 0.9. This calculation is going to give you 0.9. This is 0. What?
0.08.
0.08. So we have 0.2 as our x value, and this is going to be 0.82. y3 is y2 plus age, x2 minus y2. You see, this becomes boring very quickly. And guess what? In certain universities, you get to do all of this on the test, 5 or 6 calculations, no calculator of any kind, not even a solar calculator with 4 operations. Yeah. So keep coding, okay? Stone Age still, right? Didn't I say education still in 1800s? Yeah. Because this is what they used to do. And if they had it like 2,000 years ago, chiseling in a stone plate, the same thing, right? Then there's no eraser. You got to start the new plate when you mess up. So what is our y3? And I'm just going to bail because I'm bored. 0.82 plus 0.1. x2 is 0.2 minus 0.82. There we go. What do we have? 0.82. I'm doing all of this without a calculator, just to show off. That's negative 0.62, so 0.062, right? Like that? Let's say it's good. So 0.3 when you advance your x, and 0.88.
Wait, why is it positive?
Exactly.
It should be negative.
I was just testing if you're paying attention, and you are, which is awesome. So the rest of you, so that's going to be 0.758.
Actually, it should be 0.8. Wait,
No, 0.6. And then you're multiplying by 0.1. That's why it's another decimal here. Does that make sense? So now we have 5.8 over here. Well, that's good. 7.58. 7.58. Good. We still need to do calculation, and I am so not going to do it for these two lines. And then you will have all 6 points. Then you plot these 6 points on the XY graph, and you draw the line through those, and that line, that curve, is the numerical solution to a differential equation. Then you can try and fit some kind of a line through it. Is it a parabola? Is it an exponential? Is it trig? Right? You will have to look at the shape of the curve and try to fit the best line. They have a suggestion of a solution that you can try to see how well it matches. And that solution is 2e to the negative x plus x minus 1. So, good luck, right? So that would be the Euler method. And to calculate the error in Euler method, you will compute the differences between actual y's and the y's you calculated. That should be common sense. But we don't have actual y's, right? So you discover a method and you test the method on the problems that you can solve, and if it works there and you know how well the method works, then you say, then now these differential equations that we don't know solution for will be approximately good, right? So there is error. And I'm going to write that error as the absolute value of, let's just say, yn minus y of xn, which is this is the actual, and this is your approximation. Now again, you can't compute the error if you don't have the exact values, right? For exact values, you would have the solution, which was the equation or a function, but then you would never do numerics if you had the other one, right? So there is error. And of course, there's going to be error because we are approximating. The question is, can we do better? And the answer is yes, in 2.5, which is called improved Euler's method, which will add layers of calculation to improve the result. And that's the game you always play. More complexity for better precision, and you use more resources and more time, or you could have some wiggle room and not have the very precise answers, which means less calculations and less time. And it's always going to be, right, the balance between those two. There is no free lunch, all right? You cannot make a method that it's going to use 3 steps and have it perfect, right? So you've seen it in Taylor series. The more terms you add, the line snakes better around the function you want it to follow. With 3 terms, it's good on a short run. With 7 terms, it's good for a long while, right? Again, more terms, more calculations, less error. And that's what the always takeaway is from any error calculation. So now we are going to take a look at 2.5 algorithm, 2.5 improved Euler's method. When we are dealing with the improved Euler method, our algorithm starts with the same differential equation. Says we still have dy dx equals some function of x and a y. So you are supposed to isolate your... also, you are noticing that this is the first order only, right? So there are different methods for higher order stuff. Don't get excited that you are done with DifEqs because you know the first order, right? Method. I did mention undergrad courses 300, right? Level numerical methods. Well, there's second order, third order, and so on. Okay, so we still have our first order differential equation with a function f of x f of xy on the right, and our initial point that gives us values for x0, y0. Where do you find your initial point? Well, in case you are baking a turkey, let's say, or chicken in the oven, right? You took the initial temperature of the chicken going in, so your time is 0 because you are starting to bake, time 0, and let's say the chicken was going right out of the fridge into the oven, so the initial temperature of the chicken is 35 degrees, all right? So you have 0, 35 as your x0 is 0, and your y0 is 35 as the initial condition for the, right? So you measure this condition in nature. I don't care what you're observing. You have the population, you have the temperature, you have, right, the mixtures. So whatever it is, measure it and be done. So now, improved Euler method with step size age. So the improved Euler's method with step size age and here is the method. First, we calculate K1 as f of xn, yn. Well, these are your x0 and y0 on the first calculation. Those are given, so you should not have issue calculating K1. Then you are running the calculation un plus 1 is equal to yn plus age K1, age times K1. Then you're calculating your K2, which is f of xn plus 1, comma, un plus 1. And finally, that will give you your y2. And that is, sorry, y2, yn plus 1, which is the next value. And that is yn plus age times 1/2 of K1 plus K2. I hope you see a little bit of a midpoint there. if you go through the proof, especially if you're a math major, read this half a page in a book prior to this. I should have a separate exam for math majors on a blue paper. Derive the Eulers method. Wow, so many people already dropped the major. All right, cool. That's it, right? And that will generate the chart of values. So all of this over here is going to spit out your x0, y0. That's given from here. I'm going to change the color actually. Let's go this wood paneling one. There we go. And then it's going to generate x1, x2, x1, y1, x2, y2, x3, y3. Remember, that is your output, ordered pairs to plot and draw the line through them. This is just going to be a little bit of, more variables, define more variables and chase. You will have to have now a larger array because you have to store k's as well. You have to store those values and use, right? Use and k's. So now your array is going to have 4 values instead of 2, but it's improved, right? So. But it still should be in a single loop. And again, as a challenge, I try to pull it off. I'm not sure if they give you, yeah, they do, 2.5 application, improved Euler, and they do give you the TI-84 improved Euler, written in BASIC as well, and MATLAB code are all given.
What was that original equation that you had? X plus y equals you just learned?
It was x minus y, 0, 1, right?
Minus y.
X minus y. So you,
0 equals.
yeah, y of 0 equals 1. So, yeah.
And number of iterations, you did 2 or 3.
We did 3.
X is what?
X was 0.
Y is?
Y was 1.
And age is?
Age was, do 0.1 so you can do the, well, your age should determine immediately because when you have the interval, right, the interval was 0 to a half, and if you have 0.1, right, so interval should, when your xn reaches the end of the interval, the program should end.
Yeah, so what would age be?
Age was 0.1 in part B. And that's the one that I didn't do all the way through. I bailed. So the code is already done, as you can see. All right, so the example in the book done for the improved is x plus y. So I'm going to do something else. You can read this one. I'll pick something from homework. Should we do y minus x minus 1 or negative 2xy or negative 3x squared y, or what should we do?
Negative 3x squared y.
Negative 3x squared y.
It works.
It works?
Yep.
Got the same numbers?
I did 10 iterations, so.
Okay.
He doesn't need you anymore.
Exactly.
So
That's the point. I'm not needed anymore. Stay home, play video games. You guys are done. That's differential equations. All right, class is over.
Wait, is class over?
All right, problem number 7 is y prime equal negative 3x squared y. Y of 0 is equal to 3. They still have the interval 0 to a half and a step size age 0.1. Now we are going to work at the improved right? The improved one, which is way more calculations than the previous one. So we might bail after 2 cycles and not do all 6, and then we'll wait for the code and see all the numbers. So the way it starts is we're calculating, well, let me first write all the specs, right? You are supposed to pick from all of this, right? You are supposed to pick that your f of xy is negative 3x squared y. You are supposed to pick out that x0 is equal to 0, y0 is equal to 3, and a step size h 0.1. So those are the specs that you are supposed to pick up by looking at the differential equation. Another thing that you can have subconsciously is that you will have to do the entire algorithm 6 times, because from 0 to 0.5, you have 5 calculations, and then another calculation at 0.5 would be the 6th one. So it's always, when you divide the interval by the step size age, plus 1, right, for the endpoint. Now, obviously, we can battle that if we just do this and exclude, right, 1/2. Then you have 5 calculations. But let's not. I mean, we're not going to calculate anyway. So that's what the software is for. First order of business for improved Euler's method is to calculate K1. Boom, K1. And that is going to be f of x0 and y0. In our case, negative 3 times 0 squared times 3, which is a 0. The next one is to calculate, you know what, maybe I should just go and say like this, for n equals 0. So the entire calculation here would be for n equals 0. So now I am calculating u1, and u1 is going to be yn, which is y0, plus h times k1. In our case, y0 is 3, plus h is 0.1, and k1 is 0, so u1 is 3. K2 is f of, now, x1 and u1, because they want x n plus 1, so our n is 0 for the whole calculation here, n is always 0. So when you see n plus 1, it's 0 plus 1. F calculated at these 2 values, so we have f is negative 3, x1 is what? 0.1, right? Squared. And u1, which is our y, becomes, right, it's 3. We are plugging in u1 for y, and u1 is 3, so all of this, and we're getting negative 0.09. Very good, negative 0.09. And those are the correction terms that had helped. And finally now we can calculate y1, right, which is y0 plus h times the average of k's. Y0 is 3, plus h is 0.1, and my average of k's, 1k is 0, the other one is 0.09, average. And I calculate my y1 as 3 plus, this is negative actually, 3 minus 0.0, 0 times 0.045, That's 3 minus 0.0045, which is 2.9955. There's our y1. Woohoo! For n equals to 1. So now, do the same calculation, except you are working off of the x1 and y1 as your xn's, right, as your input, to produce x2 and y2. So calculation for k. Now you understand why you program the computer to do this, right? You don't do it yourself. So you learn a little bit of code so you can be lazy. Technically, that's what you're doing. K1 is equal to f of x1, comma, y1. Your x1 is the 3 plus the step size, right? So it's 3.1. F of 3.1, comma, 2.9955. Oh, hell no, I'm calculating. Which is going to be, oh, why did I sign up for this? Negative 3, 3.1 squared, 2.9955. Remember when I said the candlelight, right? No calculator, yes?
So when you're solving for K2, you said that negative 3 times 0.1 squared should be 3.1 squared. So it's x1, not h.
Well, x1 would be 0.1, wouldn't it? Because that'd be the
No.
first step.
We started at no, our x was 0. You scared me so much right now. I was this close to start crying.
But then
No, this is x1 over here, and x1 is x0 plus the step size age, so 0 plus 0.1.
Next step or x1 should also be 0.1, not
It's going,
yeah, not 0.1.
yeah, the next one's going to be 0.2 now. Now it's going to be point.
When you go back down,
You wrote
You did
3.1.
3.1
yeah,
Where?
right there. That f1
in
is
the
3.1.
square.
Oh no, that was just me testing if you're paying attention.
And I think that's the first one.
Are you, so the one on top is also 0.1? Like f of 0.1?
Yeah. Make sure that both of these are 0.1, not 3.1, because I took y value by accident. Your step size age increases x value. So if x0 is 0, then plus 0.1, x1 is 0.1, x2 is going to be 0.2, x3 is going to be 0.3. So that's what we have. And then we plug in all of this. So you can punch this in the calculator.
Negative 0.089865.
And there's your K1. Great. Now the next step is to quit and go learn coding, okay, if you don't know it. Should I make you either learn coding or you do this by hand, no calculator?
I'm happy if I can. Write the assembly in your notebook.
How about we waste the rest of the class and the Monday next week to compute all of this, all the way through 0.5? Let's go to 2. Just to prove a point that you should learn coding. Rudimentary coding. It's not a coding, right? You're not going to be coding, you know.
I'm writing my notes that you're coding.
Just write one loop.
Programming for business majors.
Programming for business majors.
U2 is going to be y1 plus step size age times k1. y1 was 2.9955 plus step size age of 0.1 times k1, which was negative 0.089865.
Oh, sorry.
Please.
Yeah.
You want user input?
User input.
You brought this upon yourself.
Yeah, I should have done what every good instructor does.
And done
You
this
just plug in the formula and let's go, chapter 3. Instead over here.
You know what you could have done is you
I'm
could have
screaming
had this
inside.
like written out before we got here, and just
Oh, have it on a PowerPoint slide.
yeah,
2.9.
just so you don't have to struggle
How
through
many
it right
decimals
now.
do you want?
Let's do 7. No, I'm just kidding. 98665.
6.5.
As we know. There we go.
Nailed it.
We have U2. Time to calculate K2, which is f of x2, U2, thank you, which is going to be negative 3. X2 is 0.2, right, because we go step up, squared, times U2, which is 29865.
Y2.
Y2 is the last one. So next is Y2.
Oh, yeah.
Because we are using U2 here. We need you.
Oh, yes.
You are the integral part of this operation over here.
Negative 0.3584.
3584.
Yeah.
That's our K2. Thank you. And now we have our Y2. Y2 is going to be Y1 plus age, step size age, times the average of K's. Our Y1 is the good old Y1 from before, 29955. There we go. Plus step size age of 0.1. And now we get to average our K's. So that's going to be negative 0.089865 minus the 0.3584 divided by 2. And that gives us our Y2, which is the value that goes in a chart.
.9733.
3. Thank you.
Wait, for the height, is it 0.1 or 0.2?
Age is always 0.1. Xn is the one that increases every time because xn plus 1 is xn plus age. Age is fixed. His fixed. Age is fixed. There we go. Age is fixed to 0.1, where the x's, x0 is 0, x1 is 0.1, x2 is 0.2, x3 is 0.3, because every time I need to add age, because that's what advances us to move a little bit on the x-axis and compute y. Move a little bit on x-axis, compute y, and that gives us a series of points so we can draw the line through. So this time you still have your array for x1s and y, right? Sorry, xn's and yn's, and you need 3 variables, k1, k2. They don't have to go in array. You can put them in the array, but it's always going to be. We actually can override k's because we do not have to display k's in our answer. If you want to keep all of the k's along the line, you can store them in array. So you can store all k1s, all k2s, and all un's, right? You can also store them in array, but because we don't have to display those answers, you can override them in the code, right? So you can just have a variable for it. That's what I'm saying. Even though that values will change with every calculation. So that's going to be up to you if you want to store them, but we don't need them. What we need in the output is the list of x's and y's, which are ordered pairs, which are the dots that we connect with the line, and we call that a solution to our DifEq. X advances for your calculations by adding the step size. The smaller the step size, the better the precision, right? But then more calculations. So if you have a 0.1 step size on a 1 unit interval, that's 11 cycles of calculation, right? If you put step to be 0.1, that's going to be 101 of these, right, chunks to compute. So you have to be, right, figuring out. Now remember, for computer, every operation is going to be a calculation. So your code depends on you having the best simplified algebraic terms, because the software, right, the speed at which you get to work on the computer doesn't depend only on how good your hardware is, right? It also depends on how well optimized the code is, and that primarily means reducing the amounts of calculations, which is the algebraically speaking simplified algebraic equations, so you can, right, so computer can plow through them faster, right? If the computer is going to do 100,000 calculations, if you could have your algebraic equation have 2 operations less in the whole process, you just saved 200,000 calculations, right? So you have to understand that, you know, it's going to be 1,000,000 calculations in one of these, right? Now, that's what the processor, right, is rated, how many calculations it can do per second. So,
Billions of cycles.
yes, well, in billions of cycles per second, yes. But the trick is that you want to make sure that you are that you know that every single, there is a square over here, right? So 1, 2, 3. So this line has 3, and it has to store the number, right? And you move to the next line, 1, 2, 3, 4, right? And you have to store the number. And now you have to do that 100,000 times, right? So you just have 1,000,000 right there. You get that, right? So you have to be thinking about that as well, because you do not want to put a step size of 0.1 and then wait 25 minutes, right, to get your points back. So when you code, you have to take that into consideration. Oh wait, no.
5 minutes.
It's 5 minutes.
Yeah, you were really upset that we were still here for another hour. You were really upset.
We're not solving differential equations. So I'm going to go through Ranjikara method in a good old fashion. So now you just plug into the formula. The answer is yes, but well, how about that? You can all use the code you used on the test. There's not going to be a problem for you that you can all use your
Write
code.
the source code out.
I had a class like that. Yeah, I'm not even joking.
That's cancer.
Oh.
Write out your source code. What? No. Oh, I ended up looking up the integration factor
Touching my buttons.
proof,
Why are you doing that?
where they
Yeah.
just said, because they call it move on the video I was watching.
Why?
Yeah.
But yeah, that's
No.
the
Euler's method also.
Of course.
Ian, what are you
What are you
you animal? Stop it.
It's not that bad.
But he's not even doing it in rainbow order anymore.
Oh, well, you can fix the order.
Oh, I am not going in order.
He's gonna fix it like he fixed the cabin.
No, because the
Stop.
colors are not following the rainbow.
Ian, what are you?
All right.
So with you.
2.6.
So incorrect. It's wrong.
It's wrong. If you're gonna do that, you gotta do it right.
We have 4 minutes for this, so let's. let's do this. So we now discuss a method for approximating solutions, the same. This one is considerably more accurate than improved Euler. So Euler is the basic, then improved Euler, and then this one is even better, right? And this is about 150, about 100 years, 120 years old, this method. So we just advanced, 150 years ahead, right? Two German mathematicians, right? And we can use the fundamental theorem of calculus plus the Simpson's rule from Calc 2, put those together into a method that would improve on both of those previous methods. Now, there is no per se algorithm. It goes and calculates 4Ks, and then you calculate your y, and you calculate those in a Simpson, if you remember. So let me write the iteration here, and then we'll see, right, what we can get here. So K1 is f of xn yn, same as improved Euler. K2 is going to be f of xn plus 1/2 age, comma, yn plus 1/2 age K1. Then, yes?
You said 1/2 ln K1?
No ln, age.
This is the algorithm.
These are age, step size age. All of there are no ln's anywhere. It's age times K1. K3, f of xn plus 1/2 age, comma, yn plus 1/2 age times K2. K4, f of xn plus 1, comma, yn plus age K3. And finally, yn plus 1, yn plus 1, which is the new y you're computing, is the old y, which is yn, plus age over 6, K1 plus 2K2 plus 2K3 plus K4. And end of loop. You are storing again only x and y's in array, and this intermediate constants k 1 through 4 you can override for every next loop, right? There will be different values, so you can keep overriding those. Clearly, this calculation is going to be probably twice as annoying as the improved Euler, 8 times as annoying as the original Euler, right? and with
You're not gonna
more
inspect this
components.
by hand, right?
Not by hand, but I hope I see a code for this on Monday, right? Because in life you make the choice, right? It's not, guys, I can't put this on a test and ask you to compute the problem 45 minutes in Ranjikara method. But you have to understand that your tests are irrelevant. It's what you know, right? And if you can't compute something for your engineering, whatever, then you're useless in a workforce. You write the code, right? You write the code for this. So I'm hoping to see code on Monday. I hope you code it so you do your homework and not sit there and punch your calculator for 40 minutes, right? To multiply this by hand. Wait, no, that was perfect.
I know. I have to fix this. How did you get it to stay earlier?
Bro.
You gotta do it.
Got that special touch.
This one moved.
This one moved, and I think this one.
He's just trying to get you knocked over.
Are you proud of yourself, Jess?
So, that's actually pretty good. Anyway, where's the cotton candy?
This is gonna actually, I'm gonna put this on the
College
story.
Center.
Do you want me to put my pencil?
Yeah.
When the class is too boring. When the class gets boring.
Time to take that fat nap.
When the class gets
Hold on, how's the
boring.
cotton candy for you?
Just one of my.
How's the cotton candy
Yes.
for you?
He started doing it, and then I just had to make
So,
it go in order.
Yes.
Yeah,
Because
because
he
can't do it not right.
He like
For some
put the
reason,
blues
I
over
scheduled all
there.
your office hours. I have no time to come in like between classes.
He would
And
red,
I
orange,
play softball
yellow,
here, so like 3 to
green,
5. I have
purple,
it,
or
and
pink.
my
terrible.
hours
It was
are, and
terrible.
I also
I'll give you the source code.
a basketball team, which is literally Tuesday and
Euler
Wednesday
Method.
nights.
We're gonna
I'm gonna take this fat nap in science. I'm gonna study physics later.
Yeah.
And how's
I'll study with you. I need to make my sheet.
And then
I'll do it after my nap.
I'm sorry, you need Euler's method.
Yeah, I was struggling on my homework, and
How many lines
I
of code
was,
was the
I've been working on the last couple weeks.
So I guess we're gonna Skype at like 1 a.m.
With a little bit of beautification.
I
feel
was
like a
wondering
big
if you
frustrating
recommended like the
sugar.
tutoring center or something like.
Well, no, I mean, all of this stuff is online, so you can like rewatch it
Yeah, I've
a few
been
times,
looking over
but yeah.
everything.
And I only have it, it's just